And then, so today I published the module. So let me go ahead and share the screen. And we will take a look at that. And so we'll go here. And we're going to move on today and talk about materials engineering and chemical engineering. And, you know, you can kind of follow through everything here. Most of the stuff that we're going to do today is kind of contained within this module. And so there's kind of supporting material, and we'll go through that together. We also have a guest coming in at around 4:30. So when she arrives, we'll let her kind of take over the discussion for a bit, and then we'll come back. So wherever we happen to be stopped at that point, we will come back and just continue. So let's, with no further ado, bring up the slides. Which are, man, this video thing always hides whatever it is I want to see. All right, so we're there. So I think you guys in different classes have all talked at one time or another around the ideas of chemical engineering and materials engineering. Is that right? Have you guys talked about that when you talked about the fields of engineering?
Yeah, a little bit.
Okay, so do you remember anything that would help you understand the difference between chemical engineering and materials engineering? So the way I kind of think about it, so first of all, you should probably know, I should probably disclose this, like materials engineering is really my specialty. So I have both an undergraduate degree in mechanical engineering and material science and engineering, and then a master's and a PhD in materials engineering and material science. So the way I really think about it is that chemical engineers are really experts at duplicating molecules. So let's say that you have a very complex molecule like well, I mean, honestly, like a vaccine. Like, how is it that we produce a molecule that can interact with the body? Like, how is that process done? And how can we efficiently and effectively produce many, many duplicates of molecules? And that's the specialty of chemical engineers. And so chemical engineers can work in basically any industry you can imagine that involves chemicals. And so that could be, but that, you know, that could be cosmetics. That could be, you know, beauty products. It could be food science, and, you know, all the kind of modern day non-meat, meat-like products, right? That's a lot of that is food science and chemical engineering. So material scientists tend to focus more on kind of the structural materials. So, you know, what is it that makes these scissors behave the way they behave versus a rubber band? Like, there are ways that we can characterize and define like the behavior of steel versus the characteristics and behavior of rubber. So that's really what we're going to be exploring today in our project. But first, let's go through this little slideshow. And it's kind of set up like, I think it's Jeopardy. I think that's the one I'm looking for. So, so there's kind of this question, and we're looking for that blank. And so, when we consider these questions, what are pencils made out of? What is food made out of? And what are people made out of? What are some of the answers we might have to that question? And if you want, you can put it into the chat. You don't have to turn on your mic, but.
Organic matter or synthetic?
Okay, so yeah, like organic matter or synthetic matter. And really the question or the answer I was looking for is atoms, right? So if you look at what synthetic materials are made out of, or synthetic matter or organic matter, and you keep asking like, what are those made out of? Eventually you get down to this concept of an atom, right? And so atoms are the material world building blocks of everything that we know, whether it's, every physical thing, whether it's, well, just look around, look around you and you the concept in science is that all of that is made out of atoms. And atoms, of course, are made out of their own things, right? They're made out of electrons and neutrons and protons. And so we know atoms are made out of things, but when we think about it as chemical engineers and as material scientists, we're usually trying to figure out, how can I get the atoms to arrange themselves in a pattern that is helpful to me or helpful to humanity, if you will. So then let's go a little further and ask these questions. Like, why does gas burn? Why does food give you energy? And I have to move the chat, but what is unique about gold? So what are some answers to that? Does anyone know from other classes or have other ideas? And again, don't worry about being technically correct. That's not what this is about. It's just about kind of the discovery of, all of these fields. I see that Nicholas wrote stardust, which is absolutely true. It takes, there's only a few kinds of atoms that existed in the universe before the first supernova produce kind of the heavier atoms. Anyone wants to venture a stab at, any of these questions? So, what defines the relationship between atoms? Why do some atoms interact and some atoms not interact?
Isn't it charges?
Yeah, it has to do it. Certainly the charges of the atoms or the ions that are involved. So the charges, their electron clouds. And really what I'm getting at here is the science of chemistry is really about understanding those relationships so that we have predictability about how the atoms will behave. So, unlike these little magnet balls that I have here. So, these are this is a little set of little magnet balls, and these, are all kind of connect together, and they're, they just stick because they're magnets. So I can take these and manipulate them and say, oh, I'm going to put one here and then this one, and I can fold them around and I can twist them and make these shapes. And, there's a bunch of things I can do with these because I have my hands and I can manipulate them individually. But when it comes to atoms, how much smaller is an atom than one of these little magnet balls? Anyone have any ideas?
Way smaller.
Yeah, they're like a millionth of this. So if I wanted to figure out like how many atoms went across one of these little magnet balls, it would be like a million of them lined up all the way to get across. So they're really small. We don't have a lot of technology that allows us to manipulate atoms like that. So with chemistry, we basically, and material science, we have to figure out how to use indirect means, like to change the environment to get the atoms to do what we want of them. And so usually what that has to do with, and going back to these questions from before, is, gas burns because it is storing energy that if you bring basically natural gas or propane together with oxygen in a heated environment, the oxygen will combine with the carbon and produce CO2 and produce water as well. So you end up basically going through a chemical reaction. And that's why that happens. The same thing happens inside our bodies when we eat food. We need energy. And you literally, when you hear the word calorie, that's literally a measure of the energy that is contained within that food. And then your body tries to go through a chemical process. Well, it's not just your body, it's like all the bacteria in your belly and all the things that are going on there. And basically, it's a giant chemical factory fermentation process that distills the necessary biochemicals to keep us running, right? And a lot of that, if you go through does anybody remember that term, the Krebs cycle? And yeah, so there's a whole process of biochemical reactions that allow us to function as beings. So what is chemistry? So that's kind of where we are in this. And then we're going to move on and kind of talk about all of the different atoms that we have available to us. So it turns out there's not as many as you might think. If we look at the numbers here, the biggest number on here is 114, and the hydrogen is number 1. And that's really a count of the number of protons that are involved in it. And there's patterns that develop. And so you'll see over here on the right-hand side, you have helium, neon, argon, krypton, xenon, radon. These are different kinds of gases. And then there's certain characteristics that are common in each of these. So when we talk about something like table salt is Na, sodium chloride. So you have your sodium over here. Oops, I didn't mean to do that. Oh, look, I have a pen I can draw. Sure. Will it draw? No. Not on this screen. So anyway, you have sodium over here and it combines with chlorine over on the other side of the chart. And so there's a whole bunch of relationships that help you predict which chemicals will combine with which chemicals and which atoms combine with which atoms. And it helps us as engineers figure out how to define chemical processes and define equipment to allow the atoms to kind of get together in the patterns we're hoping to see. So there's kind of like this many kind of different Legos, if you will, in terms of the world. And they're all, each kind of atom, and they're different, some are rare, some are common. But this is really the building blocks of all matter that we know about. If we look at chemical formulas, so, there's basically different ways that we represent chemicals. So if I say sugar to basically anyone that speaks English, they're going to know and have in their mind an idea of what sugar is. They've all had it at some point. And so the common name, we use sugar. That's what we call it. The chemical name for that is sucrose. And there's the way that chemical name is put together tells us information about the actual atoms that are involved. So you can see there's, well, you may not know this, but the way that this works over here is that there are 12 carbon atoms, there's 22 hydrogen atoms, and there's 11 oxygen atoms involved in sugar. And you'll see that everything in this list, all the common names, vinegar, vitamin C, alcohol, antifreeze, aspirin, these are all chemicals that are only made out of carbon, hydrogen, and oxygen. And just different numbers of them and different ways of putting them together. So we have the common names, which most people understand and know. We have these chemical names that are a little more descriptive and they're very specific. And a chemist would know how, from the name itself and the way the name is constructed, something about the atoms that are in it. But chemistry is even more complex than just this, because it turns out that atoms are three-dimensional objects in and of themselves. So if we look at these three chemicals, vinegar, alcohol, and antifreeze, you'll see that there's not only a common name, a chemical name, and a formula, there's actually like a 3D model, a 3D shape of that chemical. So if you look at vinegar, right, you have these three hydrogens that sit out and are attached to this little dark atom that is the carbon. And then you have these two red atoms, which are the oxygens. And so one of those is bound to the carbon, the other one is bound to the carbon and has a hydrogen on the side. So if you look at this chemical and then you look at the one below it, you'll see that this back shape stays exactly the same, right? So the only difference between vinegar and alcohol, and this is drinking alcohol, not like isopropyl alcohol, this is ethanol, is that you can see this, there's the common carbon, oxygen, hydrogen here. It's in both of them, but this extra oxygen over here got pulled off and replaced by two hydrogens. So if you look at this chemical and you look down at the antifreeze chemical, you'll see on one side you have this, and on the other side you have that. It's rotated, right? But basically these three hydrogens over here on the left-hand side somehow get removed and replaced by this. So, I mean, just knowing anything about these chemicals, like about their real world, you know, behavior in the human body, right? You don't want to drink antifreeze ever, never, ever. Vinegar, you can have vinegar. It's, you know, pickles have vinegar in it. Vinegar comes from all sorts of fermentation processes. It's not toxic. You may not like it, but it's not toxic. Ethanol is technically toxic. The only reason that most human beings survive their interactions with ethanol is that they manage how much ethanol is available to their body. And, you know, so when people drink too much, right, that leads them to get sick. And certainly if they drink antifreeze, they will definitely get sick. So I just kind of wanted to show that it's not just about like the ratio of the atoms, like how many carbons you have, how many hydrogens,
Question.
also how they're laid out in space.
Can I ask something real quick?
Of course, yeah.
Why does the 3D shape of vinegar, why does one of those oxygen molecules have 2 bars and every other molecule have 1 bar?
That is what we call a double bond. And what that means is that carbon has 4 electrons it will bond with another atom with. And if you look at each of the carbons, there's a connection with the other carbon, right? And then this is connecting 3 hydrogens on one side. And so that double bond just says that that relationship with the oxygen involves 2 electrons. And so the bonds on this carbon here are 2 to the oxygen, 1 to this other oxygen, and 1 to the carbon behind it. And that does have significance in chemistry. If you can imagine, like the single bonds, you could rotate the atoms, but with the double bond where you have 2 things, if you try to rotate them, the nature will resist that. And that, I don't know if you've ever heard of protein folding, or, you know, there's a lot of like complexity in how these things behave. And sometimes the difference between how a chemical works in the body is really just how it's folded up, because they can change shape essentially.
Okay, thank you.
Of course, yeah. And feel free to ask questions anytime. I see there's something in the chat. Let me check that. Yeah, the double bond. Yeah. Okay, so let's move on to the next page and think a little bit about this idea of chemical reactions. So in common language, almost everyone at some point has taken vinegar and baking soda and mixed them together. Has everyone done that at some point, or watched someone do that? What is the result? Well, I was going to say it's a foaming mess. So I wasn't looking for any sort of scientific term. I just know that it makes a big kind of foaming mess. But if we want to know what's really happening on the chemistry level, what we have is acetic acid, and it has this kind of three-dimensional shape, combining with sodium bicarbonate, and the atoms swap around. They change. You can see you can kind of see in this molecule, the NaC2, the sodium acetate molecule, how that might have come from the other molecules here and how they're swapping parts and how this water molecule gets split off. And so you have basically sodium acetate, water, and carbon dioxide. So the reason that it foams is because you have a gas in there, and that gas wants to expand and leave the area, and so it creates the foam. And then the rest of it is left behind, the water and the sodium acetate. But, and again, you're not going to be tested on any of the specifics here, but the idea is just that when a chemical engineer is trying to define a process to get to a final product, they can't just like Legos put it together. They have to find a series of chemical reactions that will take what we call the reactants over on the left-hand side of that arrow, and it will naturally go to what's on the right-hand side, which are the products of that reaction. So this is, kind of what I had talked about before, but let's just let's look at it all here. So chemical engineers often take chemical reactions and scale them up to a large manufacturing process. They focus on the production of products formed through a chemical reaction. This is sometimes called process engineering. So like I was saying, when you're trying to produce something, and it could be soap, it could be like, I need to produce a new kind of cream rinse for your hair after you wash it. And you know what chemical you want. Well, how do you get there? And that's what process engineering is, basically defining the set of chemical reactions that take you from the original reactants all the way to get the product that you want. And so chemical engineering is also, it's often like a liquid process or a gaseous process. Water desalination is an example. There's a lot of chemical engineering that is basically separating and working with oil and petroleum, because that's not a single kind of molecule. It's a very complex mess of molecules. And so if you've ever driven by an oil refinery with all the towers and the big, the big round spherical tanks and all of the stuff that's going down in those refineries is basically to separate the individual molecules from the other ones. So sometimes they're making molecules and sometimes they're figuring out how to separate them. Because even in this example that we had here, let's say that I wanted this sodium acetate. Well, the question is, how do I separate it from the other stuff that's here? So that's sometimes a challenge that chemical engineers will take on as well. Let's see, I want to check the time. I have a phone for that. Let me see if Isadora is here. Not yet. Okay, just wanted to check. Okay, so we'll keep going. Environmental engineering, oftentimes involves things like chemical engineering, because you're trying to ameliorate, right? Like lessen the impact of, say, an oil spill. So a lot of times you aren't directly just trying to clean up all the oil and collect it. You're trying to force it through a chemical process that will make it more compatible with the environment. So environmental engineering often includes things like chemical engineering. And so, whether it's the catalytic converter inside your car that's trying to make sure that all the reactions that come from the gas and mixture with oxygen through our air, that those are fully combusted, because a lot of our problems come not from the desired reaction, but the
Stop by
incomplete
Ernie's.
reaction. Question out there? All right. Okay, let's move on. So I kind of discussed some of these, but let's take another look. So food processing involves chemical engineering. And not always just because food is often, it's not like starting with raw atoms and then constructing food, although some food is constructed that way. But, you're often trying to separate atoms or, get through an efficient process to make sure it's purified and clean. Beverage making, bottling, environmental analysis. We talked a little bit about that. But, just even like the tests, like a COVID test, like how does that work? How does that happen? And I'm not expecting anyone to answer that, but that means that somehow you are able to distinguish the complexity of a molecule. And there's a lot of kind of engineering that goes into the process of making those tests. Cosmetics, perfumes, beauty products, pharmaceuticals, and then petroleum and plastics. And that could be both plastics that are derived from petroleum, or we could think of it as a lot of the new biodegradable plastics, or the plastics that come from biomaterials also are all going through a chemical process. I'm going to mute you, so if you want to say anything, just go ahead and unmute yourself. All right. Ooh, wow, that was a bad mistake. Don't scroll your scroll wheel on your PowerPoint presentation. So where might you get jobs as a chemical engineer? Well, there's the giant chemical companies like Dow and DuPont, Procter & Gamble. Of course, you probably know from the soap aisle and the Monsanto, giant ag company, Johnson & Johnson, a lot of medicine and kind of stuff from the medical field. Merck, another giant kind of medical firm, and then General Mills, which makes a lot of food. So I think Lucky Charms, and what else is a General Mills food or a cereal? Anyway,
basically all the cereals that are noteworthy.
yeah. Do they all come from General Mills now? Yeah, that probably makes sense.
I think they acquired them. I don't think they came from them, but I think they acquired all of them, like, like Trix and Pops and Cookie Crisp, everything.
Oh man, I'm getting hungry now.
Well, there's Kellogg's too, but is Kellogg's General Mills? I don't know if that's a subsidiary or something.
I'd have to look at that, but they're around, and especially in the Silicon Valley, there's a lot of kind of startup firms working in biotech and other companies like those biotech companies that they're starting up, they're hiring chemical engineers, so there's a lot of opportunity in California for chemical engineering. So materials engineers have a slightly different kind of just trying to move some stuff on my screen to get a better view. Right, so materials engineering and metallurgical kind of engineering, they're more about extracting, processing, refining, combining, and manufacturing natural substances to create new materials and meet specifications that would not be met with raw materials. Okay, so what does that really mean? Well, so for example, we might, if we think through like sports equipment. So if you look at bicycle frames and you went back, a couple hundred years ago and looked at the evolution of bicycles, some bicycles in the early days were made out of wood. Some bicycles in the early days were made out of steel. Those were things that were common materials. As we've moved forward, we've seen bicycles that are made out of aluminum. We've seen bicycles that are made out of carbon fiber. And the thing that's driving sort of that advancement of the whole bicycle kind of field is parallel to the materials field, because engineers are always looking for materials that are stronger, lighter, stretchier, stiffer, stickier, more insulative, transparent, biocompatible, semiconductive. Like, you can list all of these things that we know about materials, and there's always kind of a search for a new material that will produce and behave in a way that is unique or gives someone an advantage. So, the reason that we're going to carbon fiber frames for competitive bicycling, whether it's, well, basically in any sort of competitive sports environment, you see carbon fiber all over. What is it about carbon fiber that makes it so suitable for sports equipment?
It's really light, strong.
It's very light, it's very strong, and it's very stiff. And those are the big reasons that you see it used all over the place in sports equipment. Is just those, that kind of trio of it's strong, it's light, and it's stiff, which means the thing about stiffness is that, especially in sports equipment, that usually means that it won't absorb a lot of energy and lose it. It'll like, it might store it for a moment, and then it releases it right back to the environment to be used again. So when I think about hitting a golf ball with a carbon fiber, with a golf club that has a carbon fiber shaft, it will tend to have a farther range than a steel shaft because of all those things. It's lighter, stronger, and it's stiffer. So it doesn't lose as much energy in that interaction. And so that's a lot of why you'll see kind of high-end sports equipment, or even high-end, like heck, anything at this point, like, phones, you're seeing a lot of specialized materials in phones. Does anybody know what, my phone's cracked, so, but does anyone know what the glass is that's on the front of the phones? Has anyone heard that name?
Gorilla Glass, or are you talking about just like the actual composite?
Well, the glass itself is a kind of glass called Gorilla Glass, or variations of the kind of Gorilla Glass is a Corning. There's a company called Corning, and they made all the probably the ovenware that your grandmothers used. It's white. It has a little like flower pattern on it, and they used to bring it out of the oven. Well, that was something, you didn't have any sort of glassware that you could cook with for a long, long time. It took basically an engineering revolution for us to have glass that could survive temperature shocks. So if you've ever heard of Pyrex, has anyone heard that term? Pyrex? Like a measuring cup, a glass measuring cup is made out of Pyrex. And that's because it's a kind of glass that's specially designed so that when it shifts directly from being cold to hot, it won't shatter. Other glasses will shatter. So sometimes if you accidentally take like just a drinking glass intended for cold beverages and it interacts, it gets hot, those sometimes will crack. But back to Gorilla Glass. So it turns out, like, the story is that, I don't, it's one of those mythical stories about invention. So the story is that when Steve Jobs was carrying around the first iPhone while he was testing it, he was meeting with the CEO of Corning, and he was complaining that his keys in his pocket were scratching his phone. And the Corning guy was like, yeah, I think we have some special glasses that types of glass that we invented back in the 1960s that might help. So Gorilla Glass was an invention from the 1960s that sat on the shelf waiting for something that needed it for, almost, close to 40 years, maybe a little over 40 years. And then all of a sudden there was a need for it, and it fit the need. And Gorilla Glass, the thing that it's very, very good about is it has some flexibility and it doesn't tend to crack the way that other glasses do. And there's a very specific kind of reason that happens. As a material scientist, I could tell you how that happens, how they did it and stuff. I've given presentations on it. But for here, we just want to note that oftentimes when you're in other fields of engineering like mechanical engineering, the thing that is sort of preventing you from taking the next leap is the materials. You don't have the right material. It doesn't provide the performance that you're hoping. So we end up kind of getting stuck there. And that's what materials engineers are specialists in, is like in trying to find a combination of materials or a composite that will give you all of the properties that you're hoping to get. And, you know, here's some of the things I mentioned, like Pyrex. You can see that that's less than 100 years old. Before that, you wouldn't see glass in the kitchen, really. Not for cooking or not involving cooking. Teflon, of course, you've probably heard. There's Kevlar. There's nylon, neoprene. You can see everything on here, and it's kind of, you realize like a lot of this stuff is not that old. In the big picture, right? It's not that old. It's kind of a newer field of engineering. And down here in the bottom corner, you're seeing some kind of the biomimicry that we've taken advantage of. So there's kind of the Velcro, the idea of Velcro, right, has these little hooks. One side has these little hooks and the other side has this kind of loop. And when you combine them, the hooks kind of grab into the loops. And when you have hundreds or thousands of hooks and loops, it sticks well enough that you're able to have that connection maintained. A couple other things here, nanotechnology. So nanotech is usually requires some sort of material science because you have to figure out how to manipulate atoms on a very small scale. So, you know, here we see a tiny, I don't know, is that a flea? Maybe a flea. And you can see it's in the vicinity of these tiny little gears that were printed. And this was all doing using techniques that are used to make semiconductors and chips and things like that. So that's where we've really pushed down the scale in which we can build atoms. And so like a modern transistor on like an Intel i7 or i9 or even i5, like any of those processors, they're small. Like a transistor on those is on the order of, you know, like 9 nanometers. So again, like a 100,000th of a millimeter. And so it took a lot of engineering and a lot of hard work basically to be able to manipulate atoms to get them to go where we want at that kind of tiny scale.
How do you literally even form things that small, like a laser or something?
You know, there was early on in the process they were trying to use lasers and things to try to arrange atoms, and you can in very small quantities like really lift up individual atoms and kind of manipulate them. But the way most chips are made, believe it or not, is sort of more akin to how silk screening works. So what you do is you put a mask. And at silk screening, basically you take an image and you use a photo process to like put that image on a screen, like literally a silk screen, and you have resist. And so when you squeegee the ink through, it'll go through the empty spots and not go through the filled spots. Well, most chips are made through a really intricate process of using masks, deposition of material, and then etching and other processes. But it basically is built up layer after layer after layer after layer until you get to the complexity of a modern kind of semiconductor structure. But it's not really done directly with, it's done sort of in mass. It's like you make this big screen for the whole wafer of chips, and then you project through it. You'll send atoms through it using chemical vapor deposition, a whole bunch of other different techniques. But it's actually more like silk screening, I would say, than it is like picking up and kind of manipulating things or burning them off with like a laser. But those techniques may eventually find their time. It's like anything else. There's a lot of different efforts that people have gone through to try to achieve certain goals, and sometimes it takes a while for them to become relevant. Okay, I'm gonna stop sharing for a second just so I can see people and see what's going on. Okay, so looks like I'm having some screen issues. Sorry about that. I will try to make sure that doesn't happen anymore. Let's see if our guest got here yet. I don't see that she has. So let's, any questions out there? Okay. So let's move on and just start talking a little bit about today's activity. So again, I will share the screen.
I did have a question real quick.
Yeah, of course.
I was wondering if you could talk about graphene.
Graphene.
Yeah.
So graphene, well, graphene is a carbon structure. So if you go back and like, what are different kinds of carbon that you know of? Does anybody know of different kinds of carbon? One of them is amorphous. So if you've ever like had a candle and it leaves like I don't know if you get that kind of like black soot, right? That's amorphous carbon, and that's called carbon black. And if you think about, the ultra black pigments all come from carbon black. And there's actually, again, it's one of those weird things that you would never imagine, but when I was doing material science in a lab, I was using carbon black. And so there's just like so many different varieties and sizes and like very specific ways it's created that give it slightly different properties. Okay, so there's carbon black, which is amorphous carbon. There's graphite, which you probably know from your pencils, right? The pencil lead. It's not really lead, it's graphite. And graphite is this kind of layered structure of carbon atoms in a hexagonal form. And then diamond, actually, right? Diamond is also just carbon, and it's in a kind of structure called diamond cubic, which is different than amorphous carbon. It's different than graphite, and it's different than, and it's another one, it's diamond. So graphene is another structure of carbon, which is a kind of single layer of carbon atoms that it's laid out in kind of a hexagonal pattern. And there's a whole bunch of different kind of variations of this. There's carbon nanotubes, which are, again, like a kind of lattice of carbon atoms that line up in a certain way. There's graphene. There was something back when I was in school called the buckyball, which was the first carbon-60 molecule that they were finding. So carbon is a really incredibly versatile atom. And because it likes to bond with 4 other atoms, some of those other atoms could be carbon. And we can see that even when they are carbon, there's a lot of variety in how they can organize themselves. And so there's a lot of interest in these other carbon compounds like graphene because of their unique properties and because carbon is so common. It's a very common element, a very common atom. So it's something that if you can do useful work, like I've seen that they're using graphene and kind of building new kind of transistor technology. So there's a lot of different applications for it. but I'm certainly no expert in graphene. Other questions out there?
Doesn't carbon have like a fast, or how you say it, like a short half-life, so that anything with carbon would disintegrate fast or something? I don't really know how to conceptualize it, but
Yeah, so there's something called carbon 14. I think it's carbon 14 dating, right? And what happens is there's different isotopes of carbon. So what that really means, and if we go back to our, oh, I'm not sharing anything, so that's fine. But if you go back and pull up a periodic table, which I will do right now, hold on, let me share this. You see carbon right up here, it's number 6. And so that means it has 6 protons, but it can have a couple of different numbers of neutrons and still behave like carbon. So you can have carbon 12, which means that it has 6 protons and 6 neutrons, carbon 13, which would have 6 protons and 7 neutrons, carbon 14, which would be 6 protons. It's always the proton count that tells you what element is, and it has these extra neutrons. And those are unstable, so they will decay. So by looking at the ratio of the carbon 12 and carbon 14, you can estimate how long that those carbon molecules were bound together. And so that allows us to know things like if you find an organic material like some wood out, you know, in a, let's say you find wood and it is in, you know, they found it buried in an archaeological site, you can test it and find the ratio between those 2 carbons. And you'll find that based on the ratio, you can back out the age that it must have originally been put together in wood, because there's a natural relationship between the quantities of carbon 12 and carbon 14. So by measuring how that changes over time, you can guess how long it would take. It's not really that different where if you've watched any crime shows, you know, sometimes they'll say, oh, by the temperature of the body, I know this person has been dead for 12 hours, or, you know, you're looking at some after effect to see if you can back it out. You know, so there's things we do all the time that we maybe don't even think about as human beings, but, you know, you can look at an apple and probably know whether you want to eat it or not based on its state. So it's kind of a very specific kind of change that we can track, and allows us to age things or determine the age of things. Aging things is sort of a different process. That's what we do with cheese and wine. Questions, comments out there? All right, so one more pass to see if our guest came in yet. Don't see her yet. So what we will do is I will share, but I'm going to go back and look at our class website. So what we want to do is we are going to do a few different things today. And the first one is we want to talk about this concept of, it kind of underlies all of material science. And it's this idea that how you process something leads to different kinds of structures. And those different structures lead to different kinds of performance. So we just talked about carbon, and we know there's a big difference between like the amorphous carbon of a briquette versus the carbon in a diamond, right? We know diamond to be a very hard substance. It's used industrially to grind, and it's an abrasive in industry. But it's also used as a gem, and that's because of its unique optical properties. It has a very, you know, humans perceive it as very beautiful, but that's really just because that particular structure of carbon interacts with the light in a very particular way. So that idea of kind of the shimmery diamond, that's the performance. The properties are the optical properties, the things that make that appear. So the way we process carbon leads it to adopt these different structures, and then that leads to the different properties. So the science part of it is to basically understand how processing leads to structure, that leads to properties, that leads to performance. And the kind of the engineering part of it is to be like, well, I want this kind of performance. So how do I work backwards down that line of kind of logic to determine how I might process something? Now, material science as a formal kind of science or engineering is a little late to the game compared to some of the other ones. But before it became a science, there were well, let's go back and just think about this. Like, how do we define the earliest periods of human history? What's the term we use? Stone Age, right? So what is it about, why do we use that term Stone Age?
Because of the technology that we used at the time.
Yeah, it was like at that time, it was a total revolution in basically history for any kind of animal to become so dependent on tools and to use tools so consistently. So there was a long period in human history where it's the unique characteristics of humans in that period of time was to use tools. And those tools at that time were made out of stone and biomaterials. So of course there was still wood, there was leather, there was stone, there was flint, right? So if you've ever heard of flint napping, well, I wonder if I can find this quickly. When we take a break, maybe I'll try to find it on break and show it to you. But I recently found a picture of like someone in modern day that was showing how you can take a piece of flint and basically hit it in a certain way and create all these blades. And it was just amazing to see like how many blades they made. And so in that, what came after the Stone Age? Does anybody know what the next big age was?
Bronze Age.
The Bronze Age, right? So that was a totally kind of a different transition. So we started to get into the era where human beings had figured out not just how to manipulate the materials they found right out, laying around, right? Because sure, like leather comes from animals, but it goes through a process to become leather. Pottery, it's like taking clay and cooking it, right? And there's like all of these things. But when people learned that they could go through a process to basically deoxidize metals, because most rocks, believe it or not, are metals plus oxygen. Not all of them, there's like iron oxide, so there's iron ores and other things. Well, there's a whole process to basically extract the metal from those. And so bronze was a mixture of copper, which was basically taken out of the earth as copper oxides. And it was processed to free the copper, and then they would mix it with other metals like tin or lead or zinc. There were other metals that they were able to extract. And so this was when you compare that to, just finding a rock and hitting it in the right way to get a nice axe head, right? This is it's something totally different, which is it went into, liquid metals, casting, being able to control the shape. And so it was a whole kind of revolution of engineering. What came after the Bronze Age? It's the Iron Age. Has anyone ever heard of the Iron Age? And that's when basically people started to understand how they could use iron and carbon to produce steel. And steel is as a material scientist, like Steel is an amazing material. It actually consists of two different phases, iron and a bunch of like carbon gets involved in it. So there's iron and carbon, and then it can create these other ceramic phases, and it has so much variety. You can really tweak the properties of steel. And so you had all of these ancient metal workers and people that made, swords, like the samurai sword craftsmen were like revered because they had this technique where they could reliably produce swords. And a lot of it was almost like alchemy. I mean, it's not alchemy in the sense that alchemy is, I would just call artistry is probably a better term. Alchemy is like kind of this, how do I change, lead into gold? But they were able to basically take iron ore and create a big fire in a very specific process to create the steel. Then they would sort through the steel because some had more carbon and some had less. And then they went through this whole process to make these swords. So it was only when science basically focused its energy on understanding what was going on that engineers were more capable of defining processes that would produce the structures they were hoping for because of the properties. So it's harder to go back through that and to say, I need a material that's super light, is super strong and very stiff. In other words, you could imagine that you wanted carbon fiber composites, but you didn't know how to get there. So it took engineers to basically say, oh, you want a combination of those things. How can I do that? Well, it involves looking for materials, understanding how you can combine them, how you can manipulate them to get them through the process. So this is the first kind of the concept that you need to kind of wrap your head around. Then the next one, which there's a couple of videos here, so you can watch those on your own. But the main idea is like, what are these ideas of properties? Like how, like where do they come about? What do they mean? And so I'll leave these to you guys to watch on your own because you will kind of break off into breakout rooms and you can work a little bit on your own, but have some partners to talk to because as we get on to the project, it'll be, there's a little bit of complicated, a little bit more complication there. Let me see what's going on in the chat. Okay. So there's a couple of videos here. This one is more, it's useful. It's oriented more towards younger people, but the concepts of properties are really strong there. So, what is it about wool that keeps us warm? Like why does wool behave that way? Why are some things transparent and other things not transparent? What is it that, these are the optical properties. So we use them all the time. That's light, that's strong, that's heavy, that's, slimy, that's fibrous, that, there's like all of these things that we use in common language. But when scientists need words to have very specific meanings, then we have to get in a little deeper. And this video is more kind of about sort of the science of the behavior of kind of materials in a scientific sense. And again, if I have my magnets here, and I will kind of emphasize some of these as we get a little further. Just give me one more sec. So go back and watch these. It's only about 7 or 8 minutes total, but I think they will help you in this process. I just don't want to show them on the video here because they get a little complicated. Okay, so this video you can watch, but I'm going to kind of talk through it. Actually, let's see if I can make this play in a way that's effective. And you guys can tell me if you really can't hear it or it's not going well. All right, everyone. I just want to do a short little video on this concept of processing structure. So can you guys hear that?
Yeah.
Okay, thank you. Properties and performance. So if you recall, I've been talking for a while that a lot of material science, kind of comes down to this idea that how you process something will lead to different kinds of structures. And those structures lead to different kind of properties. And remember, properties are just kind of behaviors. And those can lead to different performance characteristics. And performance can be more than just, like a property might be very isolated to a single thing, and performance can be a more general assemblage of different properties that come together and how the whole material behaves. So we don't really have enough knowledge of all of material science yet to kind of delve into this for a kind of formal material system. So what we're going to do today is think about something that a lot of people have eaten before, that has a lot of variety and how this process plays out with it, and that is eggs. So if you go through and think of all the different ways that we can basically eat or use eggs as human beings, right? Some people eat them raw. It's unusual, but it happens. We have boiled, and boiled eggs can basically run from soft to hard. We also have poached eggs, and poached eggs can also kind of run from soft to hard. And then, of course, another would be scrambled. And if you really delve into it, you'll find that there's other ways as well. You can make baked eggs. Quiche is an example of a kind of baked egg dish. And that leads to a bunch of different structures. And so to kind of address the structures thing, let's jump out over to the web. And so we'll come here, and I just did a Google search for boiled eggs. And you can see I set up a variety of tabs here. And the first one we want to look at is, as you cook eggs, here you can see a 6 minute, 7, 8, 9, 10, 11, and 12-minute egg. And you can really see how the kind of structure changes, right? You have a very soft structure of the yolk to one that's relatively hard. Then we can go on to another tab here. This is looking at poached eggs. And you can see here's a poached egg with 2 minutes of cooking, 3 minutes, 4 minutes, and by 5 minutes you start to see the yolk solidifying. And then let's just take one look at scrambled eggs. And here's an example where, they're looking at the different kinds of textures and the different things that result from being cooked in a microwave, whether you beat in some air into the eggs, whether you start the pan cold or you start the pan hot. If you add extra yolk, you can actually poach scrambled eggs. I hadn't ever done that. Or if you add some cornstarch, you'll get these different textures. So the idea is that these structures, the way it kind of ends up resulting is what I would say is akin to the kind of structures that we see with materials. And then from there, we can get in and start articulating some of the properties. So you might say that those eggs are runny, or they might be considered delicate, right? You might think of them as being rubbery. You might think of them as being spongy. Sometimes I've had some scrambled eggs that I would say seem like they were kind of slimy. Fried eggs where they're a bit crispy. And even some boiled eggs where the yolk seems sort of powdery. And so there's just a variety of ways we might describe those structures and the way that they kind of, the way we describe them using words. And then that leads to different kinds of performance. So for example, are they good both hot and cold, for example? Some are good hot, some are good cold, and maybe both, or maybe one or the other. Another kind of like overall performance thing would be how it travels. It can either travel well or poorly. So for example, you probably wouldn't make a soft poached egg and expect to bring that in your lunch. But a hard-boiled egg might work out just great. And then if we think about another kind of performance of this whole process, you know, or this whole kind of procedure of going through this, like some processes are scalable. So for example, if you are cooking for 12 people and you all want to eat together, you might go for scrambled eggs because you can cook easily a dozen scrambled eggs all at one time. Whereas if you're going to make those poached, it might be quite tedious to try to get through that whole process. So I hope this gives you a good idea of how this plays out in a not, it's certainly a material system, eggs, but we're just more familiar with it in terms of the kitchen and in terms of eating. So thank you. So I just didn't want to have to, I've tried to do that. That's the most efficient I've ever been, where I could get it done in a kind of quick amount of time. But the one thing I will say about that is that when I was talking about steel, like steel is almost as versatile as eggs, believe it or not. Like the subtle things you can do to change the behavior of steel. I don't know if anyone has ever watched that show, Forged in Fire. Has anyone seen that? It's
Is that about the guy with the really weird beard who can make massive swords?
yeah. So it's kind of an interesting show to watch, especially as a material scientist, because you know, like the guys that are kind of grading them on their ability to make something, every once in a while they're like, "Oh my God, what are they doing? They're quenching it. It's, you know, it's like glowing white hot. It's gonna break," and you really start to learn how steel behaves. And some people, you know, they're, you know, it's kind of an amateur competition. But, you know, there's mistakes people make and you can't recover from them once your steel is embrittled, because when you put stress on it, it will break rather than kind of survive. So it's a pretty fun show to watch. I toyed with the idea of trying to watch some of it today, but I would encourage you to go watch that show at least once. It's kind of interesting from a material science perspective. But steel is amazing. Steel is almost as versatile as eggs when it comes to just change a little bit about how you process it and it comes out totally different. I saw that there was a question, and you can make scrambled eggs in the microwave. You don't want to start in the shell. Yeah, you don't want to do that. I've done that. That was an unwise decision when I was young. It gets really messy and stinky, by the way.
It
All right.
does taste different. I've tried it.
Oh, yeah. I wouldn't be surprised if it tastes different. Yeah, and the texture is probably really odd too. But a lot of times, like one of my favorite bagel shops, when you get like an egg bagel, they microwave the egg. That's how they get it. That's how they cook it.
That just sounds like the laziest thing to do, because eggs are already so easy to make. So it's like you're just trying to make it even easier.
Yeah, I think what they're doing, especially with the bagel sandwiches, is they want it in a very specific shape, so they can put it in a little container that's that shape, put it in the microwave for 30 seconds, and then it's just like flop it on, it's ready to go. But yeah, it's interesting if you, when you start to, as you like live in different circumstances, you know, so like I've lived in circumstances where, you know, you don't have access to a kitchen, but you have access to a microwave, and you get really, you get really creative about the things that you can achieve with it. Okay, I see a chat thing going on here. Let's check that out. Oh yeah, the solar ovens. Yeah, solar ovens are pretty amazing too. It's not going to be a class project. It's one, I've done a few solar projects at Cabrillo, but the weather is so inconsistent that sometimes you're counting on the sun being there and then it doesn't show up. All right, I am gonna take one more look for our guest. And I have a feeling that she forgot about today's meeting. Maybe when we're on break, we will, I'll try to check in with her and see if she can make it. All right. Let me clear up some of these windows so I can keep going. So we're going to look at a certain class of properties. So that concept that you have processing that leads to structures, that leads to properties, that leads to performance is very general for material science. And that can affect mechanical properties, which we're going to talk about here. But it affects optical properties, it affects magnetic properties, electrical properties, acoustic properties. There's a whole bunch of different sets of properties, but we're going to focus on what are called mechanical properties. And mechanical properties are ways of understanding how the material will respond to a load. So for example, here I have a rubber band. Let's hold it against the wall here. So when I put a load on it, which just means in this case, I'm stretching it, it will extend itself. It changes its shape. But when I let go of it, it'll return to its shape. If I take this set of magnets that I have here, and I kind of form that into a shape, I can rearrange the shape and it will take on the new shape. So just like clay or other materials, some of them will return to their original shape and some will change shape. Another example would be a paper clip. Generally speaking, a paper clip looks like this, and when you use it, you put some paper in there, it uses its elasticity, its ability to return to its original shape, because when it's like this, it's a little bit distorted, but it holds the paper together because the material is wanting to go back to its completely flat thing. But when this is pulled out a little bit, I hope this can kind of show, it's like when it gets sprung out like this, it'll return. It wants to do that. So it's holding the paper. But if I abuse the paper clip, in other words, if I take it and bend it too far, it holds that new shape, right? That's what we call plasticity. So materials can be both plastic in this form, right? This is kind of a technical term. It doesn't just mean like, oh, this is made out of plastic. Plasticity is the ability to take on a new shape. And so metals are very good and they're helpful, and that's part of why the Bronze Age and the Iron Age existed, is because they were it was easier to shape those things than stones, right? Like stone is pretty hard to shape, and it's pretty hard to shape and get a sharp edge, so those two concepts, elasticity and plasticity, you'll see there's other ones here: stiffness, ductility, brittleness, strength, resilience, toughness, hardness. And the reason I'm not going to go through all of these with you is because the project is basically to go through each of these, this list, and to look for things in your house that exemplify them. So something that is very elastic versus something that is not very elastic, something that is very plastic versus not very plastic. So for each property, you're looking for two things: one that exemplifies it, like it's at its extreme, it's very high, it's maximized, and one that's at the other end, which is like it's minimized. So when you go through that list, and this is why I think it's really helpful to be with other students in a breakout room, is because you have to kind of talk sometimes to like understand the subtlety of these properties and what does it mean for it. What is, like strength is a pretty easy one to imagine, like this is strong and this is not strong. Well, how do you define that? How would you quantify it? So the idea is to go through this list and go through that list and try to find things in your house and, that exemplify it. And so that's really the task of today's project. And then there's another discussion forum that will do a similar thing. I'll show you that. And I really want you to try to not just use your mind, not just imagine something that is, ductile versus something that isn't. I want you to try to find real things. Because I think once you have that real thing in your mind and it really fits the property, you'll never forget that property again because it'll be attached to that item. So try to have something physical in the physical world. And you can, look in your house, like the kitchen, the garage, wherever, wherever you are, whatever you have available to you, the bathroom, like your toothbrush, realize that everything around you is made out of atoms and could probably serve to some degree in this role of being a reasonable thing to look for here. Okay, so that's one project that we're going to do. And then the next one is, okay, so this is just, Maseo is a former student and he wasn't able to make it, so he made a video. And so that's one of your assignments. And you can say it's due, you can do that outside of class. You don't have to do that in the breakout room, but listen to his video, follow through here, and you're asked to just post a question or share something you learned from his video. And then the other kind of materials thing is this discussion, which is, again, focusing on processing structure and properties, but it's looking at something like, I took out these scissors and I wrote this little paragraph here, which is I'm trying to connect the ideas of properties and performance. So you can see I said here, they probably selected stainless steel blades because it is hard and keeps a sharp edge. Stainless steel is corrosion resistant, so it is not likely to rust. The polymer handle insides are soft and pliable, which makes them more comfortable for the user. Because, and just, you can pick things from around your house. Like, here's a stapler. Like, why is there a plastic housing out here? Why is it made of metal? Like, why is this made of metal? Why is it not made of plastic? And trying to tease out, like, in terms of this paradigm of processing structure, properties, and performance, why those decisions were made. And then your reply to other classmates would just be to, that there might be another reason that they did it. So like, here's an additional example. Like, I bet they chose to use plastic handles because plastic is easier to form into complex shapes, which makes them more comfortable. Or that, don't forget about cost. A lot of these decisions are made about like cost or availability or, to lower the price to compete in the market. So there's a whole bunch of different ways this can fit together. And again, this is not due tonight, it's due later. In fact, it's obviously got the wrong due date. Let me go fix that right now. Oh wait, I have to leave student view. I always manage to somehow forget something. No problem. It's easy enough to change them. But if you find anything like that that just seems wrong, just let me know and I'll fix it. And I got to get this out of the way so I can save it. Okay, so let me stop sharing, check in with people. How's it going? Any questions, comments? Do you kind of know what you're after, what you're trying to do? I'm going to assume silence means that everyone totally understands what to do. So what I'm going to do is, oh, good, I got a thumbs up. Yay. Multiple thumbs up. Life is so good. Oh my gosh, they're just like everywhere now. I'll go ahead and stop the recording and maybe, I think it's probably a good time to take a break. So let's take a 10-minute break and come back at 5:35. And then we'll break out into groups and start to talk about what the properties might mean and then try to find those items that exemplify them. And if our guest shows up in between, then we'll allow her to kind of talk to us first. All right, so I'm gonna go ahead and stop the recording. Actually, I'm gonna pause the recording.